While local exhaust is very effective at removing contaminants generated in kitchens and bathrooms, it isn't adequate to remove contaminants generated in the rest of the house, and it only runs when the occupants turn it on. With the tighter buildings being constructed these days, it's sensible to include a ventilation system that runs continuously at a low to moderate flow rate to ensure good air exchange. The latest building codes call this whole house mechanical ventilation. ASHRAE 62.2 calls it whole building ventilation. Current residential codes address the use of whole building ventilation, but it's only required in particularly tight houses. The flow rate required by the IRC in those tight houses is based on the floor area of the dwelling and the number of bedrooms. A table is included that allows the required rate to be easily determined. The rates on this table are the same as those required by the 2010 version of ASHRAE Standards 62.2. But ASHRAE 62.2 requires a mechanical ventilation system in all new houses, regardless of how tight they are. Of course, this isn't code, so it's not required by law. But if you're participating in a program that specifies compliance with ASHRAE 62.2, like Energy Star Homes or Lead for Homes, then installing the ventilation system is required, and it must deliver a flow rate that's calculated based on a formula in the standard. The fan-driven ventilation rate required by ASHRAE 62.2 2013 is based on two factors: the total desired ventilation rate and the amount of that rate provided by infiltration. We'll call the fan rate CFM fan, we'll call the total desired ventilation rate CFM total, and we'll call the infiltration rate CFM infiltration. That's close to the nomenclature used in the standard. So the overall equation is CFM fan equals CFM total minus CFM infiltration. ASHRAE 62.2 2013 includes an equation for CFM total, and it's based on the floor area of the dwelling and the number of bedrooms. Here's how I put the formula into words. The total desired ventilation rate is equal to 3 CFM for every 100 square feet of floor area, plus 7.5 CFM for each occupant, assuming that there are 2 occupants in the master bedroom and 1 in each other bedroom. It'd be better to use the actual number of occupants, but for new construction that may not be known until after the house is built and put on the market. The CFM infiltration, which is called the Infiltration Credit in the standard, is determined based on a blower door test on the completed house, and it can't exceed 2/3 of the CFM total. There's another calculation for that, and we'll get to it in a few minutes. This method of using the blower door reading to determine an infiltration credit specific to each house is new to the 2013 version of ASHRAE 62.2. Recent versions applied a standard infiltration credit to each house and rolled it into the formula. In the 2007 and 2010 versions, for example, the credit was 2 CFM per 100 square feet of floor area. This new method is challenging because the fan must be sized when the house is being designed, but the blower door reading isn't known until the house is completed. I've spoken with some raters working with builders on projects, and they often tell the builder to install a fan that meets the requirement without an infiltration credit, rather than trying to guess at what it might be. The assumption is that the builder or homeowner can lower the speed of that fan based on the actual conditions in the finished house. Does it actually work out that way? I'd guess that very often it doesn't. The result may be a house that's overventilated with all of the associated issues I mentioned in an earlier lesson. So here's our formula. We can break this formula into 2 steps. First, we'll calculate the total desired ventilation rate using the base formula, and then we'll calculate the infiltration credit. With those 2 numbers, it's easy to calculate the CFM of airflow the fan must deliver. Let's apply this to a sample house. It's a simple ranch with 3 bedrooms and about 1,200 square feet of living space. It's being built in a new subdivision just outside of Trenton, New Jersey. This is a pretty tight house too. It's in the New Jersey Energy Star Homes program, so a rater has been visiting the site to make sure all of the air sealing details are correct. So the blower door reading is just 850 CFM at 50 pascals. Our first step is to plug the information into the formula for the total desired ventilation rate. The first part of the equation deals with the floor area. So we multiply 1,200 square feet by 0.03. That gives us 36 CFM to ensure good air exchange based on the house size. The second part deals with the number of occupants, which we'll estimate based on the number of bedrooms. So we multiply 3 bedrooms plus 1, 4 potential occupants, by 7.5. That gives us 30 CFM to deal with the contaminants generated by 4 typical occupants. So we need 36 plus 30 for a total of 66 CFM of desired ventilation. ASHRAE 62.2 2013 also includes a table that you can use instead of doing the calculations. You just find the row that includes the size of the house and the column with the number of bedrooms. Where the two intersect, it lists the required CFM, which is 75. Notice that in this case the number is higher than what we calculated. That's because it does the calculation based on the highest possible floor area in that row. So in our case, the house is 1,200 square feet, but the table calculated for 1,500 square feet. The standard has us overventilating again. Remember, that number we just calculated is the total desired ventilation rate, but some of that is satisfied by natural air leakage. So the next step is that we get to apply an infiltration credit. We know what the blower door reading is, 850 CFM. But that's the leakage rate at the 50 Pascal test pressure. We need to use that blower door reading to estimate the leakage under normal, natural conditions. To do that calculation, we'll use two other pieces of information we have, the local climate and the height of the house. If you've worked under an energy efficiency program, you've probably used a simple formula to estimate the natural air leakage from a blower door reading. This method first came into use in the 1990s, and it's still included in the BPI Building Analyst Standard. You simply divide the blower door reading by an N factor. The N factor is obtained from tables that always take the building height and geographic location into account. They may also take the shielding into account. We expect more natural leakage from houses that are taller, more exposed to the wind, and situated in colder climates. Researchers are continually trying to make the estimates more accurate. ASHRAE 62.2 2013 references the calculation methods in ASTM standard E779. I'm sure the resulting estimates are an improvement, but this standard presents some challenges. The blower door test must be done in both pressurization and depressurization, and it must be a multi-point test ranging from 10 to 60 pascals. Then all of that data must be crunched down to get a single number estimating the effective leakage area of the house. The sample calculations take up 4 pages in ASTM 779. That's a little more work than I think we can justify on each house. Not to mention the challenge of making sure that each auditor knows how to do it all correctly. Fortunately, ASHRAE 62.2 allows authorities having jurisdiction the option to approve a simplified calculation method. It specifically mentions the method included in the ResNet Mortgage Industry National Home Energy System standard. Most programs have adopted or at least accepted the simplifications included in the ResNet calculations. In some cases, this is explicitly stated in the program documents. In other cases, it's implied in the sample calculations. BPI includes this simplification in BPI 1200. When I first went through this document in detail, I was bewildered by the complexity of the calculations. It took phone calls to ASHRAE committee members and calculations filling a significant portion of a legal pad for me to figure out how this simplification is justified. I won't torture you with the math, but I certainly wish the ASHRAE committee would explicitly endorse the simplification in the standard, rather than requiring calculations and testing that no sane architect, energy auditor, or rater would go through on every single house. In this lesson, I'll use the simplified calculation method. It states that the infiltration rate at natural conditions can be estimated as CFM infiltration equals 0.052 times WSF times S times CFM 50. In this equation, WSF is the weather and shielding factor from table B1 at the end of standard 62.2. S is a factor accounting for the height of the building, determined from table X1 in the standard, and CFM 50 is the blower door test result in cubic feet per minute at 50 pascals. Running the entire calculation every time leaves a lot of room for error. If you're going to be doing the math instead of using a software tool, it'd be worth investing the time to create reference tables that simplify the data for your region. For our example house, the weather and shielding factor is 0.48. The closest weather station is Trenton. The S factor is 1 because it's a one-story house. If it were 2 stories, the S factor would be 1.32. Now we can plug those numbers into the equation. The estimated natural infiltration is 0.052 times the weather and shielding factor of 0.48 times the S factor of 1 times the blower door reading of 850 CFM. That gives us an estimate of 21 CFM. That's our infiltration credit. We now have all the pieces needed to calculate the required fan size for this house. The base formula gave us the total desired ventilation rate of 66 CFM. The infiltration credit was 21 CFM. When we combine them, we come up with 66 minus 21, which equals 45 CFM. We need to install a fan that can provide at least 45 CFM of continuous ventilation. ASHRAE 62.2 is very clear that the calculated ventilation rate applies to the final delivered ventilation rate of the installed system, not just the manufacturer's capacity rating for the fan. The flow rate of the installed system must be measured and demonstrated to be capable of meeting the ventilation requirement. In order to reinforce these calculation methods, we've included some practice questions in this lesson. You'll need to use these three formulas to complete them, so please write them down so you'll have them available. And hang on to them after you're done. You'll also need them to complete the 10-question quiz at the end of the course. Hit the pause button now if you need more time to write them down.